Section: Introduction. In this section, we delve into the privacy concerns linked to using large language models, LLMs, especially in federated learning, Florida, and embedded vector databases. Our aim is to investigate the risk of third-party services or malicious model providers reconstructing original text from text embeddings, which could jeopardize user privacy. We are motivated by the increasing use of LLMs in handling sensitive data within collaborative learning setups. To address this, we introduce Embed Parrot, a novel approach that conducts input reconstruction attacks on systems by leveraging their latent representations. Embed Parrot utilizes a transformer-based architecture to understand the complex relationships between input data and their hidden states, thereby probing the vulnerability of such systems to revealing sensitive information through obscured model representations. Our contributions are twofold. Firstly, we propose and carry out a comparative analysis of various embedding inversion techniques, such as base embed inversion, fine-tuned embed inversion, hotmap embed inversion, and embed parrot. We assess their effectiveness in reconstructing the original inputs of CHATGLM6B and Llama 2-7B using a comprehensive set of metrics. Secondly, we investigate the impact of token length on reconstruction performance. Our experiments demonstrate that Embed Parrot consistently performs well across different token lengths, showcasing its stability as a reconstruction method. We also test Embed Parrot across various datasets, revealing that its performance is influenced by data distribution but is not limited to a specific distribution type. Furthermore, we propose simple yet efficient defense mechanisms to prevent the misuse of Embed Parrot. These defense strategies provide practical ways to safeguard against malicious exploitation of embedding reconstruction capabilities. Through thorough experimentation and systematic analysis, our work contributes to the ongoing discussions on securing LLMs against emerging privacy threats in federated learning environments. Section Summary. In this section, we delve into the privacy concerns surrounding large language models, LLMs, in federated learning and embedded vector databases. We investigate the risk of third-party services or malicious model providers reconstructing original text from text embeddings, posing a significant privacy threat. Our work introduces Embed Parrot, a novel approach utilizing a transformer-based architecture to probe the vulnerability of systems to disclose sensitive information through hidden representations, offering defense mechanisms against potential misuse. Section: Preliminaries. In this section, we will explain the key concepts related to language models. When we talk about language modeling, we are essentially trying to figure out the likelihood of a sequence of tokens occurring together. Modern language models, like the ones based on the transformer architecture, have a large number of parameters, often in the millions or billions, denoted as theta. These models start by converting input tokens into a series of vectors using a word embedding matrix W. These vectors are in a space represented as R(V, XD), where V is the size of the vocabulary set V, and D is the embedding dimension. The model then calculates hidden states, denoted as H_I, which depend on the tokens that came before them in the sequence. These hidden states capture the context of the sequence up to that point. The transformer architecture uses multiple layers to refine the representations of the input data, creating intermediate hidden states. Each layer processes the outputs from the previous layer, starting with initial embeddings derived from the input tokens. The hidden states undergo transformations through a multi-head self-attention layer and a position-wise feed-forward neural network in each layer. These transformations are crucial for capturing complex patterns in the data and generating abstract representations necessary for language processing tasks. To understand how a tokenizer converts the hidden representations from a transformer model into text, we introduce a series of functions that describe this process. We start with a function called logits, which maps the final hidden states to a vector of logits using weights, W, and a bias term, B. Our goal is to reconstruct the original input text from the hidden states of a specific transformer layer. We present three methods for this: base embed inversion, BEI, hotmap embed inversion, HEI, and embed parrot, EP. BEI relies on the hidden states from the last layer of the transformer to predict tokens and recover the original text. HEY focuses on maximizing cosine similarity within the embedding space of a pre-trained language model to find the most similar vocabulary word to the hidden states from a specific layer. Embed parrot addresses the challenge of reconstructing the original input from deeper layers by training a specialized model using the transformer architecture. This model generates output embeddings similar to the initial hidden states, which are then combined with HEY or BEI methods to produce an output closely resembling the original input. Section Summary. In this section, we delve into the foundational aspects of language models, particularly focusing on the transformer architecture and the generation of intermediate representations through multiple layers. We introduce three methods: base embed inversion, BEI, hot map embed inversion, HEY, and embed parrot, EP, aimed at reconstructing the original input text from hidden states of a specified transformer layer by leveraging innovative techniques like maximizing cosine similarity and training a lightweight model to restore hidden states effectively. Section: Datasets. In this section, we utilize two FIN-GPT training datasets, FIN-PT Sentiment and FIN-PT Fika_Ka, as well as a subset of the Wikitext dataset called Wikitext2 Raw v1 for our study. The FIN-PT Sentiment dataset is for sentiment analysis in finance, containing 76.8K data lines, while the FIN-PT Fika_Ka dataset is for training question answering models in finance with 17.1K data lines. The Wikitext2 Raw v1 subset consists of 44.8K lines of curated content from Wikipedia. We split these datasets randomly, setting aside 20% of the data for separate test sets. We mainly use the training data from FIN-PT Sentiment and Wikitext2 Raw v1 to fine-tune our models and evaluate different text restoration methods on the test sets. Our experiments focused on two transformer-based models, Llama 2-7b and CHATGLM6b. Llama 2-7b is a language model optimized for dialogue tasks, with 32 layers, a hidden dimension of 4096, and 32 attention heads. CHATGLM6b is a language model with 6.2 billion parameters, 28 layers, the same hidden dimension as Llama 2-7b, and 32 attention heads. We evaluated our methods using various metrics, including Rouge 1, Rouge L, F1 score, and Sentence BERT score, to assess text reconstruction and semantic similarity. Our results showed that the base embed inversion, BEI, method performed differently on CHATGLM6b and Llama 2-7b, with CHATGLM6b showing better performance overall. The hot map embed inversion, HEY, method improved text reconstruction metrics for both models, especially in the initial layers. We also introduced the embed parrot method, which outperformed BEI and HEY in deeper layers of the models. Embed parrot trained on the FIN-PT Sentiment dataset showed the best performance on similar datasets, with slight variations in results for different models. Integrating perplexity, PPL, into the loss function did not significantly improve model performance, except for datasets with longer token sequences like Wikitext. Section Summary. In this section, we utilized three different datasets for training our models: FIN-PT Sentiment for sentiment analysis in finance, FIN-PT Fika_Ka for financial question answering, and Wikitext2 Raw v1 from Wikipedia. We trained our models, Llama 2-7b and CHATGLM6b, on these datasets and evaluated their performance using metrics like Rouge and F1 score. Our results show that the embed parrot method significantly improves text restoration for both models, especially in deeper layers, showcasing its effectiveness across different datasets and model architectures. Section: Impacts of sequence length. In this section, we examined how the length of sequences affects embed parrot using three different datasets. Our findings are summarized in a table. We noticed that for CHATGLM6b, Embed Parrot struggles more with shorter texts compared to longer ones. This could be because ChatGLM6B's architecture captures relationships between tokens better, making embeddings of longer sequences contain more meaningful information for Embed Parrot to work with. On the other hand, in the case of Llama 2 to 7B, the impact of sequence length is not as significant, as performance remains consistent across different lengths. Even though there is a slight decrease in certain scores within a specific length range, the overall semantic similarity remains stable. More detailed analysis on additional datasets can be found in the appendix. Moving on to our defense strategy, inspired by previous work, we introduced a new technique to safeguard the privacy of input embeddings. This method involves using an overlap matrix along with the discrete cosine transform, DCT, and its inverse, IDCT, to hide sensitive features in the embeddings. Starting with an input embedding in a certain dimensional space, we create overlap matrices based on random permutations of indices. These matrices are then used to transform the input embeddings using DCT and IDCT operations. By dispersing the original information across different frequencies and selectively retaining or dropping information based on the overlap pattern, the transformed embeddings become more secure while still being useful for model processing. The overlap matrices are saved to ensure consistency in applying the transformation during various stages of model development and evaluation. Our defense results show that for ChatGLM6B, applying the transformation to later layers is more effective in reducing Embed Parrot's reconstructive abilities compared to applying it to the initial layer. However, this approach also slightly affects the model's generative performance, increasing its perplexity. On the other hand, for Llama 2 to 7B, transforming the initial layer has a similar impact on reconstruction but causes less harm to the model's generative capabilities. These differences highlight how ChatGLM6B and Llama 2 to 7B respond differently to defensive strategies, even when facing similar challenges.